I'm Nathan Ireland.
And I'm Dylan Windsor.
I'm Claire.
And this is our passive filters video.
Enjoy.
In order to do this experiment, we first had to figure out where omega fit into the equation so that we could try and predict what would happen when we changed the frequency. Being that it's a simple circuit, it was a simple voltage divider equation, and we could try and figure out what omega would look like between the resistor and the capacitor. Turns out omega ends up in the denominator of the result, which would lead us to believe that when omega increases, the denominator gets really big, resulting in a decrease in voltage. So before we actually plug wires into anything, we simulate with LT Spice, as always. Here you can see our low-pass filter with the capacitor leading the resistor. This is a 1 microfarad capacitor and a 1000 ohm resistor. And I'm going to be doing a sweep from a frequency of 11 to 10,000. Here's the graph of the simulation. We start out very close to 1 volts, and you can see it drops down continuously as the frequency increases and starts to level out and will eventually become 0 as omega tended toward infinity. Now with my high-pass filter, I have the resistor leading the capacitor, and you can see that I start out with a lower voltage, and as the frequency increases, the voltage does as well, and eventually planes out very close to 1 volt as the frequency tends toward infinity.
This is our low-pass filter setup on this half of the circuit. And on the other half of the circuit here is our high-pass filter setup. On the low-pass filter setup, we have a capacitor and a resistor in series. This is the power input from the power source, and that is connected to the DAC here, this is the output. This is outputting a voltage here, and then this is modulating the frequency here of our input.
The DAC assistant feeds output voltage to the function generator, which continually increases the frequency. And down here, the DAC is measuring the voltage in and the voltage out. When we run it, you'll see the white represents the V in and the red represents the V out. So you can see as the frequency increases, V out gets smaller compared to V in. And we're going plaid.
They've gone to plaid!
And here's the Nyquist plot. The Nyquist plot is going to represent the change in voltage due to the change in frequency. Now when you're using polar coordinates, a sine wave would actually just be a circle around the origin. And so what we see here is that the voltage starts out more in the real direction and decreases with increase in frequency towards 0. And this, being that it's circular, indicates that it's somewhat sinusoidal, just like we saw when we were in LT Spice.
Alright, here again is our VI. The block diagram is here. Start it running. As you can see, we're under the high-pass filter, which means the red, which is our V out in between the resistor and the capacitor in our circuit, is constantly getting larger as the frequency of the input gets larger. The Nyquist plot is generated here, which is a upward facing half circle.